advertisement. So can you see my screen and me? No problem?
Yes, it's perfect.
That's good. So okay, thank you very much. Thanks everyone for coming to this seminar. So the title of this talk is Calibration-free wall-shear-stress measurement technique using a dual-layer Hotfilm sensor. So there are three students make contributions to this work. This is Liu Shenhe, Wang Hao, and Dr. Julia Li. And they are all in Dalian University of Technology, which is the previous university I worked at. So so right now I'm working in the Harbin Institute of Technology in Shenzhen, which is the third campus of the university, started 20 years ago. It's in the south part of China, right next to Hong Kong. And then this is the original place, Harbin Institute, the Institute of Technology. And this is, here is Dalian. I'm not sure, can you see this? This is Dalian, where this work, all this work was done. And actually, currently, I'm physically in Dalian. So we had a Center for Turbulence in Shenzhen, which is headed by Professor Zhou. And you probably see some of the familiar faces here. And Bob Antonia came here every November, not the previous one. Hopefully next November, he will come. Today, what I'm going to talk is a measurement technique for wall shear stress. And then what makes this unique is it is a calibration-free technology, means we don't really have to calibrate. And I made a bar here. We finished some of the initial work, and then some of the work, we have done some preliminary work, and it's not really fully done. And hopefully in the future, what we're looking at, we can have a real calibration-free and fast response, which can two components, which can measure the vector of the wall shear stress, and can also good for air and water and multimedia, and it should be reliable. So in making it short, I'm really looking forward to developing a technology that can measure the wall shear stress as simple as temperature measurement. So probably most of you have used thermocouple before. Now we have a gauge, we have a thermocouple wire, and we plug it in, and the temperature come out. And hopefully in the future, we'll have technology like that. And today, the only acronyms I'm going to use is WSS, which stands for wall shear stress. So wall shear stress, Riskstrike is very important. So if you're looking at the passenger airplane, 50% of the drag is the Riskstrike. And then the wall shear stress, which is actually directly related to the Riskstrike. And then if you look at the drag force of an underwater vehicle, such as a submarine, 60 to 80% of total drag is actually Riskstrike. It is so important, but however, we don't really have a reliable method to measure the wall shear stress on the real vehicles. We do have some of the technologies that we can use in the laboratory. For example, we can put a force balance, something like a floating device as a part of the wall. And then you can monitor the really fine strain of the balance. So this is reliable instrument that a lot of people has been carrying out the similar work, these kind of work in laboratory. However, it's not convenient for a real vehicle. The same thing that it's actually applied to the direct measurement of the velocity profile. As we know that the wall shear stress is the product of the viscosity and the velocity profiles near the wall. So we can actually directly measure it with the help of a microscope. We can actually resolve the velocity profiles near the wall. But again, this is doable in laboratory, but it's not convenient in the actual, you can't really apply this on a real vehicle. And there are other methods such as a pressing tube where you use a really fine total pressure tube and position it in the viscous sublayer. So, and then you can use some empirical correlations. This, you can get the mean velocity well, but you can't use it to measure the dynamic wall shear stress. The Hotfilm sensor, however, it's able to measure the dynamic. It is simple to use. Basically, it is a thin piece of metal film that attached to the surface of the wall that you want to measure. And then by applying the DC currents through the film, it generates the Joule heat. And the Joule heat was taken away by the fluids. And in the literature, you can find the 1/3 power of the wall shear stress will be proportional to the convective heat transfer. So by using this relationship, we can measure the heat, and then we can get the wall shear stress. There are different kinds of commercially available shear stress sensor, the wall mount sensors. These are from the Dentec from Europe, and these are TAL system actually from the States. But there are some problems there. If you look at the thermal conductivity of the fluids and compare it with the substrate, for example, if you have a steel wall, the thermal conductivity of steel is more than 100 times larger than the thermal conductivity of water. And if you are working with air, this is even worse. So the heat, the Joule heat generated by the film, most of them do not go to the air, but actually goes to the wall. So this will make the problem really hard to work with. So if you put the sensor in somewhere you know the wall shear stress, and you do a calibration, and you will have a calibration curve like this. That means when the wall shear stress goes to 0, you still have a large intersect here. So this intersect B, people will argue this is actually related to the heat loss. The more loss you have, the larger intersect you will have. So because of the fact that more heat was lost than transferred to the fluids, so people argue that calibration of the constant A and B doesn't really work. You calibrate it, and then you put it in real use, and then you will find that A and B will change. So different calibrations will give you a different set of A and B. So that's why people are arguing calibration is not unique. If a calibration is not unique, that means you're in trouble. The calibration is not valid. You can't use it. And then there are different kinds of technology come up, try to minimize the heat loss so that we can use it. So there are air cavities. So there are vacuum cavities. There are different kinds of passive technologies try to minimize the heat, but you can reduce it. But the heat loss was never reduced to 0. There are ideas that has been bring up by researchers. So for example, like this, people say if you can put a guard heater, so there's a second heater. If you can maintain the two DYs at the same temperature, say by T top equals T bottom, and then whatever generated by the top will not goes to the wall. So this is a very interesting active insulation technology. And then in Treaty et al. It's actually demonstrated this will work. They demonstrate this using a numerical simulation. So the problem is how to make it real. So after this really long 15 minutes introduction, now I came to the contents of my talk. So my talk will have these 5 sections. So these are the answers that we have to the problem. So we propose a 2-layer hot film sensor, which have 2 hot films attached on 2 sides of a non-conductive, a non-electric conductive film. So basically, so this is hot film, and then on both sides, we have a metal film attached to it. And then the 2 films, actually a nickel film, their thickness is 2 microns. In the streamwise direction, it is 1.7 millimeter. And in the spanwise direction, which is across the film, is 20 millimeter long. So to make these 2 films working at an identical temperature, so we connect each of the film into a Kelvin bridge. So 2 films, we need 2 of these bridge. So these bridge, this bridge is similar to the Wheatstone bridge. However, this is a 4-wire lead. This is 4-wire bridge. That means on the sensor, on the hot film, there are actually 2 sets of wires. One set of wire connects the hot film in the bridge. And then so when we put this in the bridge and we change the settings of R1 to R4, so these are 4 potentiometers, we can change its resistance. By changing these resistance, if the bridge goes to balance, the sensor film RU, its resistance RU will be set by the potentiometers. So by set the working resistance of the film higher than its cold resistance, we actually heat it up. And then the temperature of the film was totally determined by the potentiometers. So by changing these potentiometers, they will increase the temperature. And then if you compare the 4-wire Kelvin bridge with the Wheatstone bridge, their difference is dramatic. The Wheatstone bridge only have 2 wire. Both the sensing lead and the source lead are the same set of wire. The bridge will also go to balance, but however, the Kelvin bridge will set the film temperature at much more accurate temperature than the Wheatstone bridge. And this 0.1 Celsius uncertainties in temperature makes a lot of difference in, this is actually one of the core technologies of this method. If we use the regular Wheatstone bridge, this will not work. I will explain why this will not work later on. So by putting the 2 wires in 2 sets of Kelvin bridge, we set their working temperature precisely the same with an uncertainty of plus minus about 1 Celsius. It's actually 1.4 Celsius. And then we take the hot wire sensors and we put in a long pipe facility. In the long pipe facility, we know exactly the shear stress near the exit, the exit of the tube. So by putting the hot film at a location where we can change the shear stress and we know the shear stress, we can do a calibration. And then we can see whether our active insulation technology will work. So this is the results. And then the x-axis is the wall shear stress at the location of the sensor. So it's where the wall shear stress we set. And then the vertical axis are the heat transfer, the Joule heat generated by the upper film divided by the temperature difference, which is the temperature of the film minus the ambient temperature. So we see by varying the the sensor temperature, and then presenting data in this way, and all these data falls on, most of the data falls on the same line. And we look at the intersect, and it go roughly to 0. So that means that the technology, the activity installation technology actually worked. There are no heat loss through the substrate. Nearly all the heat generated by the upper film goes to the air instead of, there's no loss. So by comparing the data from Bell House, and then you can see there's a large difference over there. So one more thing we do is we take the data, our data we have, and now it's presented in a dimensional way. If we present this in a non-dimensional way, so basically we normalize the wall shear stress and the heat transfer using a proper way, in a proper way, and we can find that, and most of the data actually falls on the same line. That means if RE tau, the Reynolds number based on the friction velocity, is larger than 40, and all the data falls on equals the same value, which is 0.9. So this is actually not unexpected. This is expected because if you're looking into the literature and people are actually talking about this, so as long as like 70 years ago, people actually had a model of the thermal boundary layer under the turbulent boundary layer. They solved this by assuming the temperature profile is similar. So they can find this. So it's similar, but our data is a little bit off. But this tells us that the heat transfer and the wall shear stress actually have a very clear, well-defined relationship. We can use this equation once we measure the heat transfer, that we can utilize this equation and we can calculate the shear stress. So this will become a foundation of calibration-free methods. So before we go to the real calibration methods, and let's check this, whether this will work in water. So we do a similar type of measurement. Now this time we apply this in water. This is a long pipe. The pipe diameter is 2 centimeter. And then through the loop, we can measure the flow rates. With the flow rates, we can actually calculate the wall shear stress. And then, and this is the one thing to notice that this is a bare film. There's no insulations, any waterproof technology apply on it. There's no coating. We try to make the life longer, so we use the deionized water instead of the regular tap water. And then, so we get the data. Even the data is only a few data points, but still the intersect goes to 0. The non-normalized data equals around 0.9. So this, it doesn't really matter if water and air, they all work. So, and then just as I mentioned, the normalized data equals to a single number. This gave us, this tells us that we can actually use the equation to measure the Q, calculate the tau W. So this is how it works. Basically, here, x-axis is the Reynolds number based on the shear stress. And then vertical axis is the wall shear stress. So this is actually the different flow rates. And then the dash line, black dash line you see here, are regarded as the true value, because this is we directly measured out of the long pipe. All other data are estimated using Hotfilm, and you can see that only one line is off, which is the film with a low temperature. So it means the temperature of the film is too low, it will be off. And once it's high enough, all the data will fall on the true data. So that tells us that the calibration methods will work. And with a higher film temperature, it will work better. And then, so that's the calibration-free method. So now for the vector measurement, it is, the idea is like this. So if we had if we notice the heat transfer from the hot film reduced, it could actually caused by two different things. One is the direction of the wall shear stress actually changed. It's no longer normal to the, once there is a yaw angle alpha here, as the yaw angle increase, the heat transfer will reduce. But then this is equivalent for us to have a simple reduction in the wall shear stress. So we can only measure the heat transfer. The heat transfer decrease, we cannot distinguish whether it's direction change or it's amplitude change. So to figure this out, we have to study the effect of this alpha. What's this alpha effect on the heat transfer? So if we look back into the hot wire measurements, the hot wire measurements, usually what we do, we decompose the velocity for two components. One, we decompose into the normal direction Vn, and we decompose as a tangential velocity Vn. And then we use empirical K, empirical number, which is called yaw coefficient. Usually it's 0.1 or 0.15. And this makes things really complex. And what we do for the film, we take a different direction. So basically now we analyze this problem as in the direction of the wall shear stress. Instead of using a coordinate on the film, we use a coordinate on the stress. So we cut the film into many, many small filaments, and we'll look at the heat transfer on each filament. So now, if we look at the AAVO of this film, and then we'll have a small element like this. So basically, what we have, you see the area in color is actually the thermal boundary layer. And then the thermal boundary layer is what I draw here. What the schematic says here is well under the viscous boundary layer. And then now we can do analysis of the, take a small filament, say the area in orange. We take the orange, and then we can use that as a control volume, and we can write down the energy equation, which says the energy flux change over a small filament dx equals to the heat transfer Q goes into the control volume through the boundary. And then by assuming the temperature profile is parabolic, which is typical when we do the unsteady heat transfer. And then the heat transfer came into the system is related to the temperature profile. So by solving this energy equation, we will have the total joule heat Q equals to the long equation here. So let me just go directly to the solutions of this. So what the analysis tells us is that Q divided by dt, which is the heat transfer divided by the temperature difference between the film and fluids, equals to a constant 0.9, multiply all the fluids properties, all the geometries, is the width, the length of the film, and then this is the direction effect, cosine alpha to the 1/3 of power, and tau W is to the 1/3. So, and if you look at this, what it means that for the heat transfer of a film, the tangential part of the stress. Doesn't really make any contributions at all. It's all the normal parts of the stress. So then we know that as the alpha increase, it will change with the cosine 1/3 of the alpha. With this, and then we can actually come up with a model to get the vector measurement. So next, we try to prove this. We try to validate this model. We use this is a open loop wind tunnel with closed test section. We remove part of the section wall with a turntable, and then we attach one of these hot films on top of these on top of the turntable. So we rotate it, and then here is the result. The solid line you see here is the model cosine alpha to the 1/3 of the power, and then the solid blue line dots are the current data, and then other points is some other people's data. I got from one paper, very old paper. It's surprised that it's only one guy studied this before. So this is actually, the model described this really well. So this actually, the model works, but it's only for a certain degrees to 60 degrees. If it's higher than 60, then the other factors kick in. So you can't do this anymore. And so the directional effect works. And then if that works, we take two of these films, two of these sensors. Each of the sensor will have two films. And then this sensor assembly totally have 4 films. So this is the stress. The stress will have the angle with the sensor is beta. And then the stress, the angle is alpha 1 with the first sensor, second sensor is alpha 1 and alpha 2. And then with the model we have, so we know that Q1 is this upper film, this is the Joule heat from the sensor number 1. Q2 is from the sensor number 2. And then it will have this relation with alpha 1 and alpha 2. So this equation set, this is a linear equation set. If the two sensors have the same coefficient, that means have the same geometries, and then they're operating at the same temperature, we can solve this equation. We can actually find tau W and this direction by simply measuring Q1 and Q2. So this is the solution. And then we can try to verify this if they work. Again, it's the same turntable and same wind tunnel, same conditions. So we turn this and we find that. So this x-axis is the angles that we set. It's the real angle that we set the angle. And then tau W measure is what's given by the hot film. And then tau W is what we know. So in a narrow angle range, plus minus 15 degrees, and the measurements actually works. So the amount of measurements about that is within plus minus 5%. And then the angles is the plus minus a few angles. I think it's 3 or 5 degrees. Sorry, I should put this number here. And then we do error analysis. It's about telling you roughly the same thing. So I didn't put it here. It's fairly long. If you're interested, you can look into the paper we published last year. And time is running short. So this, we actually finished the vector measurements. So let's quick summary is that we developed this active heat insulation technology. We can block the heat loss. So if we block the heat loss, that means we can use the heat of the upper film. We can calculate the shear stress. We can not only calculate the amplitude of the shear stress, we can actually have the vector of the shear stress, but only the mean value, not the fast response. So the time response is like this. this is the original bridge that we have. So if we introduce a square width on top at this location, by using the square width, we actually break the balance of the bridge. So at the moment, the balance is broken. And then the system tried to go back to the balance. So then if you watch here, and then you have some curve like this. So if we take the 63% of the peak value and count the time, it's about like 5 milliseconds. So the system roughly had a time response of 200 hertz. That means if the shear stress change, the system should catch it within 5 milliseconds. And then we try to verify this physically by putting hot film in a boundary layer. And then upstream of the boundary layer, there is a slot. And then there's a loudspeaker here, really tiny speaker, which can drive the air in and out. So basically, by applying, so for example, this is a 60 hertz of driving, of actuation. And then we can measure the dynamic output of the hot film. So they'll give us a peak at 60 hertz. So this is actually the response of the changes in the wall shear stress. And then there's a hot wire, which is located right above the hot film. And then the hot wire was located inside the viscous boundary layer. So the velocity measured by the hot wire can be interpreted as the variations in the wall shear stress. So then we scan the, we do this at from 10 hertz, from 20 hertz all the way to 300 hertz. Basically, so we scan the whole frequency range, and we compare with the magnitude of the peak. So this is the result at right of the, if you can't see my mouse, at right of the screen is the result. It's the ratio of the peak at the frequency, at the perturbation frequency between the hot film and hot wire. So what tells here is at low frequency, it goes to 1. So the roughly is the same. Hot film actually follows really well, but only to like 50 hertz. And then when the frequency goes up, the response of the hot film decreased really fast. So by it go to 200 hertz, it's ready to go down 40 dB. So that means it's only like 1/1000th of it. It's really small. And then above 300 hertz, we don't have any response of the hot film at all. So now, so by making it calibration free, we have the advantages of using it. However, we almost lose most part of the frequency response. So 300 hertz is really a low frequency in terms of turbulence measurement. So this has to be investigated in the future. Now, the last part, I will use 2 minutes to present the very preliminary water measurements. So as I talked before, we have already done some water measurements. But the problem is, if you put a metal film inside water and you pass current in it, it will corrode it in no time, basically. If you use deionized water, probably you have a longer time, but it won't be over a few hours. So if you want to make the life longer, and it has to be insulated. So then the regular technology to insulate this is using quartz, as we have the hot film before, this whole quartz. But quartz has a problem. Quartz has an advantage because it has a good thermal conductivity, which will give you a good time response. But its mechanical property is not good. It always crack. So we tried parylene. Parylene it's actually a polymer, and then this can be applied onto the sensor by using vapor deposition. And there are quite a few companies here in China who do this at very reasonable price. So and they claim they can do 500 nanometer to 100 micrometer as you wish, with plus or minus 10% of errors in it. So then in this test, we deposit 3.2 micron thickness parallel coating on it. And then, but there's a problem here. So this is the picture of this, because the parallel is transparent. So basically you can't really see it. But when you apply some a coating on it, what you change is the heat transfer temperature. T wall is no longer TU. So this will make us make the equation that we used doesn't work. So in order to make it work, we really need to know the true T wall. So we know TU by measuring the resistance. But then in order to know T wall, so we have to introduce another model. So basically what we do is we assume the temperature profile in the coating is linear. So if that's linear, Q is something we can measure. TU is something we can measure. So if the linear profile assumption valid, and then we can actually calculate T wall. Once we have T wall, and we can plug it back into the equation that we have before, so and then we can measure TW. So, and then we do a test in the water loop that I talked before. So this time, the water here is the regular tap water. And then now we do a few test points, and we find out that the true values and the Hotfilm value calculated using the model works. So the preliminary test tells us this will work. The linear profile inside the coating is valid. But then the question is, how far? We know that if it's too thick, it won't be valid. So there must be a boundary where the thickness boundary, where it tells you this is valid, this is not valid, but we don't know this yet. So this works to be investigated in the future. And then the final part of this is we take the sensor, go down to Wuxi. It's the guest. You may not know if you're not from China that in Wuxi, there are all kinds of a water facility that can go really fast velocity. The whole thing is pressurized. We can do it. We did a durability test, but it's sadly that when water velocity goes to 5 meters per second, and we find out that the sensor track down, it's about 7 pascals. But over that, and then the parallel coating was peeled off. So we failed the durability test. So that's something we're going to do in the future. We try to make it more durable. So with this, we come to the conclusions that, so we go back to the bar, and then that's the final goal, a calibration-free, fast response, 2-component, multimedia, a reliable measurement for turbulent boundary layer. And hopefully we can, in the future, after a few years, we can measure the wall shear stress. In a similar way, right now, we measure temperature using thermocouples. So get a gauge, plug it in, now you have the number. But I can't do this. I think this is the way to go, but I can't do this all by myself. So I'm looking for collaborations from the experimental fluids community. We're really happy to provide the CTA bridge. I know that there must be a lot of difficulties for everybody to develop their own bridges. So we are really happy to provide these bridges, and we have some experience in making sensors. So I'm really interested in sharing this and try to get more people to follow up on this technology, and let's make it together, make it make a difference in this field. So thanks, Dr. Zhang, Professor Fan. So that's my talk. Now I'm taking open up for questions.
Thank you very much for